Okay, let's start. Good afternoon, ladies and gentlemen. I'm Jan Lahoda, and I work for Oracle, and I usually work on the Java compiler inside the JDK, that is javac. That's the compiler that compiles Java source code into Java bytecode. And first I would like to show this statement, and then I would like to remind you that we use Slido to submit questions. And today, I would like to talk about what APIs we have in the JDK to model the Java source code and how we can use these APIs. So this terribly big slide, is an overview of the APIs that we have in the JDK for this purpose. And here at the bottom part, my mouse is not working very good, are APIs that are standard APIs that every Java compiler should implement. And there are several of these APIs. We have the real model for Java language, then models that model stuff like types, classes, methods, and so on. That is the language model here. Okay, let me try this. Then we have the annotation processing API, and we have an API to actually programmatically invoke the Java compilers. That is the javax tools API. And here at the top, we have APIs that are public and supported APIs, but that are not standard in that sense that every Java compiler would implement them. They are very specific to only javac, to our compiler. And these APIs allow us like access to the compiler ASTs to more, let me say, granular view of the source code using the ASTs. And we have also APIs that allow us to more precisely see what the compiler is doing, more precisely than the standard javax tools API or annotation processing API. And what are the uses of these APIs? There are quite a few of them, but I guess the main two for like most people is either that we can add additional constraints on our code. We can enforce some additional rules that we want our code to have by using this API to produce errors for code that doesn't match these new constraints, that doesn't follow the rules. And we can use these APIs to generate code and data. For example, we could analyze the sources for a project and generate some index for all the classes, or generate an index that would tell us which classes implement which interface, which we can then more easily load at runtime and use it to speed up, for example, startup, as opposed to searching all the physical class files, loading them into memory and analyzing them. There are some more possible uses. For example, NetBeans ID is completely written on these APIs, but I believe that these two uses are the most important for most people. And now, this is basically the only slide I have, because now we will switch to an IDE. And here on the right, we will usually have some example that will show us what we want to do, what we want to achieve. Here on left, we will have the code that does what we want to do. So the first thing that I would like to do is let us enforce a rule where which tells us that we cannot have public fields that are not final. Because if you have public field that is not final, everyone can assign to it. It may be difficult to debug. Let's try to run to code somewhere or see some verifier that will ensure that we don't have such fields. And for that, we can use one of the APIs And this API will show us a lot of stuff. And this API is the element API, where we have this interface element, and element generally describes some or models some declaration, class, package, field. It doesn't really model stuff inside method bodies, or not easily model stuff inside method bodies. It only goes to the level of methods, of method declarations. And this generic interface element has some sub-interfaces for specific kinds of declarations, like for modules, for classes, that is type element, for methods, that is executable element. It's like if it looks like a class, that it may be an interface or an enum, it's type element. If it looks like a method, that may be a constructor, it's executable element, and so on. And so we have this model that basically models the declarations in the source code. There is one tricky thing in this API that we should note, and that is that using these interfaces are like interfaces, and it's not necessarily safe to use instance of to manipulate these or to check the type of the interface, the type of the element. And the reason can be seen here in this delegating element, because we can have a class that implements several of these interfaces. And obviously, if this L would be an instance of this delegating element, then this instance of would be true. But the delegating element can delegate to something else. We don't know to what. It can misbehave if you use instance of. So the API is written in a way that we should use either some kind, which is accessed through getKind, which will return us what kind of the element we are holding. And this is the list of kinds that are in the API. So we can see if it's a field. For certain cases, there are is methods on the kind that will like group all fields. All fields are basically fields and enum constants. Classes are classes, enum send records, and so on. So if we want something that looks like a class, we can use getKind is class. We don't need to check if it's class, enum, or record. We can use this is class method on the kind. There are also visitors for elements. Also, for elements, they are not needed to work with elements, because elements normally have like, for each element we can get the elements that are under it, the enclosed elements, and the element that is above the element, the enclosing element. So we can recursively go through the tree of elements easily. We not necessarily don't need to use visitors. But visitors are also a safe idiom for elements. And now let's go back to the example with the fields. And I have an implementation of some checker here. And let's not discuss how we will get the elements right now. Let's discuss just how, if we are given some elements, how we validate if they follow the rules or not. So let's have this validate method that is given the elements that we are compiling, basically the top-level classes that we are compiling, and some way to report errors, which is this error reporter, which is not a standard thing. I have written this only for this presentation. We will see how we would report errors later. And basically, we are given the elements that are being compiled. We can put them into some to-do list, into a queue. Then we take them one after another. We validate every element, and we add all the like elements that are under it in the tree to the to-do list. And by this, we will basically walk all the element hierarchy that we want to walk. And now how this validate element method can be implemented, it's very easy for this, because we basically ask, is the element a field? If it is, let me see the modifiers for the field. Does it have a modifier public? If yes, is it missing modifier final? If yes, report an error. It's fairly easy. And we can see, for example, what methods are on a generic element. So on a generic element, we have methods to access annotations, access the enclosed and enclosing elements, modifiers, and simple name. So it has the basic methods that we need to work with declarations. And now let me just run this example, and we see that it indeed produced some error for the field that is not okay according to our rules. And for elements, because if every method that, or every feature that, or every thing that we would want to do with elements would be a method on element, it would be like too big. There are also utilities for elements that are called elements. And these element utilities have many more methods to manipulate elements, which are sometimes useful. Now let us switch to another example, and this is we have talked about the declarations, and now let's focus on types, because that's a bit different in the API, and it's actually a bit different in the Java language as such. And let's imagine we want to find methods, or we want to prevent methods to return arrays, because arrays are like mutable. The elements of arrays are always mutable. So if you would return a shared array, and anyone could write into the array, so we would need to do some copies of the arrays. It's easier to simply return some collection and not arrays. So let's create a validator to report errors on methods that return arrays. But first, we cannot do this anymore with just elements and declarations. We need actually types. And for types, we have a different hierarchy called type mirror. And it has again, several sub-interfaces. It's again an interface with several sub-interfaces. One of them is declared type. We will talk about it in a minute. Then there is array type for arrays, primitive type for primitives, and then there are like quite a few others which are special case and not that commonly used. But now let us see why we need something like declared type, why we cannot like model Java types using just elements for declaration. And the reason is that let's consider this list class. There is only one declaration, but there can be any number of types in the Java language which are concrete parameterizations of the declarations. You can have list of strings and so on. So we basically have the element as the declaration, and we have a declared type, which is a particular parameterization of that element. It is a particular parameterization of that type with the type arguments. So basically, a declared type is a type element plus type arguments with some exceptions. And for this, we really need something else than elements for declaration. We need something special that means type mirrors or types. And now let us switch to actual implementation of a verifier for methods that return arrays. And we again have some validate method that is being called as before, that searches the elements as before, that calls validate element method as before. And here it's again very similar to what we had. We look if the given element is a method. If it's a method, in this case, we actually need to have the particular element type, that is executable element for methods. And on that, we have get return type, which returns the type mirror. And if this type mirror is an array, which we again check using getKind as its elements, we report an error. And if we run this, it will hopefully produce some error. But as you can see, it will not produce an error for this case, for this thread method, where we are basically doing the same. We are returning a list of arrays, and anyone can modify the arrays. So let's quickly try to improve this by recursion, and not like this. And yeah, let's create a field. Let's create a method here to validate type. Let's use switch, and let's use the new switch because it is better. So like this, we have what we had before, and we can say if the type is a declared type, we can look in the declared types, we can look at the actual type arguments that are in the type. So I will take declared type from the return type, and I should import it and take the type arguments, and probably on another line call for each. And now I have a type argument, and I will just recursively call this same method to validate again the actual type arguments of the declared type. And now if I run the compiler again, I should get 2 errors, even for the third method. And of course, I can have like any depth of these declared types, of these parameterized types in the source code, and get the same result. So let's comment this out so it doesn't get into our way. And now, so what we have seen a way how declarations are modeled, how Java types are modeled, how we can use these. And now, so far, we were just called here with the elements that are being compiled. How do we, who will call this method for us? How do we achieve the way, or how do we ensure this method is called with the proper parameters? There are multiple ways to do it, but one of them is annotation processing. And annotation processors are, you could say, like compiler plugins. There are pieces of custom code that run at a specific time in the compilation. After the code is parsed, the elements are created, then the annotation processors are run. And they run in rounds. So first there are input files, they are parsed, elements are created, annotation processors are run. They can create new files, like Java source files. There are parsed, elements are created, annotation processors are run, and so on, up to the point where the annotation processors will not generate any new files. After that, there is one last round of annotation processing, which allows us to do some cleanup, to write some summary files, and so on. And then the compilation continues, and class files are possibly produced. So how does one declare an annotation processor? It's a class that implements this interface processor. But it's much easier to use an abstract processor, which is a class in the same package. It just provides us, it just gives us some more services. And you may also note this supported annotation types annotation, which basically allows us to specify a pattern on which annotations should be automatically searched in the source code. And only if there are annotations of the given types which match the given pattern, then only then the annotation processor will be called. If you star, it will be called always for all sources, which is what we want for these validators. We want them to run on all files, regardless of annotations in them. And the actual implementation of the annotation processor typically is in this process method, which is basically given three pieces of data, let me say. First are the annotations that were found in the source code, which in this case is not that important. Then we are given a round environment, which is a group of data that relates to this particular round of annotation processing. And in this case, it's for example the root elements, which are the elements that are being compiled in this processing round. And we can also get elements that are annotated with a specific annotation easily, which is quite useful for annotation processors. And the third piece of data that we are given is this processing environment, which is the environment of the whole compiler, basically, which is independent of the round. It holds data that are valid for the whole compilation, or for most of the, for any round of annotation processing, let me say that would be more correct. And we have, here we have access to the element utilities for types. We also have an access to something called messenger, which is here. And this messenger has methods that allow us to print errors, warnings, and so on. So this is how the error reporter was implemented. We use just messenger to print the errors. And if you print an error, it will actually stop the compilation after the annotation processing. There are also other things like filer, which allows us to access files, read them, and write them with some limitations. And we have access to options that the user may provide to the annotation processor. And so basically what we have for the validators, this is it. We just, inside the process method, we call the validators with the root elements, and it's validated. And the validators do their work, and everything works. There is one more thing that I should mention. The annotation processors need to be registered in a way that service loader can find them. So if they are in the unnamed module, it's registration in meta services. If they are inside a named module, they need to be specified in the module info, of course. And now let us see something more complex for annotation processing. And for this, let me show this example, which I admit is difficult to read. Let me try to make this bigger for a moment. We have basically, we want to read some value that is localizable to different languages. And we can do it like this. We can create a resource bundle and we can read a value of a key from that bundle. Of course, like this will work if we run this, and if we are lucky, it will actually do what we want. Of course, what happens if I write, if I break the key? Then like nothing happens up to the point where I actually try to read the key from the bundle, and I think I need to do clean build, because there is probably the bundle is somewhere cleverly cached. And now, like only here at this point, when I do getString, I will find out that the key doesn't exist in the bundle. Which, like, if this will be caught rarely, I may find this in a production or after a week or I don't know how long it will take until I find out that I messed the mapping of the key in the source code and in the bundle. So this is not nice. What we could do, there are many ways to improve the situation, but one of them is that I can use annotation processing to help me. And I can do something like this. I can say, hey, I would like a message that eventually will be put into some properties bundle so that people that do actual localization to other language can localize it because they have tools to do it in the properties bundle. But at the same time, this properties bundle will be auto-generated for me, and I will not read it from the bundle manually, but I will use something special, again, generated for me, some method that will actually read the value from the bundle for me. So I think this is nicer because first I have the information in one file. I don't have the code and a properties bundle aside. And the second thing is that I cannot easily mess this up because if I change the key here, the compiler will tell me no. You cannot call hello world method. There is no such method. There is no such key, and I actually need to do something like this, and you use the correct key basically. And this class, this newly created class, it's nothing magic. It opens the resource bundle and it returns the key for me. I just cannot easily use an incorrect key. And one thing I would like to say that for simplicity for this demo, I did it so that the properties bundle and the new Java file are created for each top-level class separately. We could do it like that there would be one properties bundle and one generated class for the whole package. It's just a little bit more difficult to do and a little bit longer, but it can be done. So now let me try to show you how the annotation processor that does this actually works. And yeah, let me first try if it works. And it does. And if I change this text here, okay, I don't know what will happen. Yeah, it actually changed. I should make a bigger change, but there is one at the end. So how does this is generated by an annotation processor. So how does this work? This works in several steps. First, we gather all the message annotations for a given top-level class so that we then can generate the properties bundle and the Java source code in one pass, because we can only write every file once in the annotation processing. So first, we basically gather a map from the top-level class to all the messages that are inside the class, which is this, and it's not really difficult. We just go through the elements annotated with message. We take the outermost element and we put them into the map. It's easy. And then we go through the mapping, and yeah, it would be nice if I could use pattern matching here. And then we basically write the properties bundle, which is easy. We just take the filer that allows us to read and write files. And if we call a method called create resource, it will create an arbitrary file for us. And if it's a resource, it will not be part of annotation processing and it will not be compiled. It's just a file that will be written somewhere and hopefully part of the result. So we create some resource file and then we just dump the keys into the file, like key value. It's easy. And then we have another file to write, that is the Java source code. And we use the filer to create source code file, which then will be subject to annotation processing and from which a class file will be compiled. And we basically do something here. It's not really that important. You have seen the result of this. It's just some basically textual manipulation to create the proper source code. It's not really difficult. And if you run this, we have this, I would say, fairly nice thing. So I think this is nice, but if you have code like this, or if you have the validators, which will be easier to show now, we can have a pretty complex code in some validators that validate some rules, or some very complex code in annotation processes that generate somehow. And we probably don't want to like test all this manually. Like I wouldn't want to test all this manually. So how do we write tests for this? And we can use another API that we have, and that is the compiler API, that is javax tools, to actually start the compiler at when we want it. And we can start the compiler, we can provide it a source code and check the output if it matches our expectations. And we can write a lot of tests like this. Basically, an example, correct output, an example, correct output. And the nice thing is that if we want, we don't need to run anything on disk during this process. It can all run in memory. So we can create, let's say, utility class or test method, a utility method or test method like this run test, which is given some sample code and the expected output. And we could have 100 tests like this very easily. And the run test method, that is like the actual nice thing here, it's not really complex. It again fits on this very small screen here, if I'm careful. And let's ignore these first few declarations, and let us focus on this get task and this get system Java compiler. So what I can do is to get this Java compiler instance that represents the compiler inside the JDK, which basically is Java C, at least under normal circumstances. And when I have this compiler, I can ask it to create a new task for me, which is the actual compilation. And the get task method has a lot of interesting parameters. Basically, all of them can be null. If any of them can be null if you don't want to specify a value, but we need to have some non-nulls, otherwise it won't work because it wouldn't do anything, obviously. The first parameter is that we can capture output from the compiler, which is like actual textual output from the compiler, which is sometimes useful for the tests, but it's better to actually capture the errors than the textual output. We can provide file manager. File manager is an abstraction that the compiler is using to read files from disk and write files to disk, or maybe not to disk. So we can use the file manager to actually like write into memory if we want. We can write class files into byte arrays and then use class loaders in memory that will actually load the class and run them if we want. So by this, we can ensure that the task will not write into disk or onto disk if we don't want to write onto disk. Or we can write into some other storage if we want. We could do basically almost anything. And we could also read from various places if you wanted to. Then we have like an interesting way, some diagnostic listener, which is called for every error or warning produced by the compiler. And we can see the implementation here. It's not really difficult. We basically take the diagnostic, the error or warning, we produce some meaningful textual representation for it and put it to the output, which at the end we compare with the expected value, and that's it. Then we can have a list of options, which are basically the same options as we could provide on command line, except we cannot provide the input files there, only the options. Classes to process, if you would do just annotation processing, we can specify the names of classes, sometimes useful, but not that often. And then we need to provide the input files that should be like compiled, let's say, in this compilation. We could use some default file manager to like map files on disk to these input files. But we can, for tests, it's more easier to create our own in-memory, like representation of file for the compiler, which is this test Java file object, which is extremely easy. We just use this simple Java file object, which is standard thing, and return the text, the code in the file in this getCharContent method, and pass an instance of this file object to the getTask method, and it will compile the file, or it will run the compiler on the file. I did a little bit trick here that I set procs only, so it will only run annotation processing and then stop, so it will actually not produce class files in this case. This is the way how I achieved that. It will not write anything to disk, it will not write the input, and it will not write the output. I could do it using file manager, but it would be longer. If I only want to run annotation processing, procs only is probably the easiest way. And when I have this getTask method, or the result of this getTask method, which is some compilation task, I can just call a method named call on it, and it will run the compiler, and it will return true or false, depending on whether the compilation succeeded or not. In this case, we expect it to not succeed, because we expect an error. We could, of course, make the method more complex to allow positive and negative compilations if you want it. So these were the standard APIs that we have for manipulating, or not manipulating, working with the Java source code. And now let us peek at the APIs that are not standard but are public in the in javac. And for that, let's us take this example here. And on string, there is method to lowercase, which maybe sometimes we want to use, but this method has small, I don't want to say problem, but there is something tricky about this method, and the thing is that it uses the default locale to actually convert the string to lowercase. And if I run this, we can see that using two different default locales, converting capital I, we here get two different outputs. We get small I with dot and small I without dot. Sometimes it may be correct, sometimes it's not. I've ran into this many times. So let's imagine we don't want invocations of to lowercase without a parameter, without explicit locale, which we can do. There is an overload of this method. Let me show it like this. There's an overload of this method that takes an explicit locale, and that is fine because it will be always, the output will be the same regardless of the computer on which we run the program. So let's imagine we want error for a code like this. We cannot do this by just using the elements and types, because the elements are not modeling really modeling the bodies of the methods. They are only modeling declarations that end at the level of methods and field declarations. So we need to go to some more detailed model, and that more detailed model is the AST that actually javac uses to compile, to model the source code, to compile it to class file. And I have a debugging view here, which shows how the AST looks like, at least a bit. And we have basically, the O is always some tree node, and there is simply a tree of things. So we have compilation unit for the whole file. There is a class inside the file. There are methods inside the class. Inside the convert method, we have this block tree, which represents the methods block. Then we have the return statement, And inside the return statement is the thing that we are actually looking for, and that is the method invocation, the place where we call the method. And these AST nodes have some information attached to them, at least after the tree is resolved, or how we call it, attributed or analyzed. It depends on the view. And so this method invocation tree node, AST node, has some information attached to it, and one of them is which method is being called here. And in this case, we see it's method to lowercase, and it's actually to lowercase on string. The element is actually the particular method on string without any parameters and so on. So if we wanted to produce error for code like this, what we would do is that we would go through the AST, we would find all places where there is a method invocation, we would look at this attribute that specifies the method that is being called, and check that whether we are calling the method to lowercase or not, and produce an error as we decide or as we need. So how do we do that? And again, I have a magical method validate that will be called from somewhere. And we may actually get to the place from where it's called. And this method is given some top-level AST nodes for the things that are being compiled, for the source code that is being compiled. And we use something called tree-path scanner, which is basically a visitor that goes through the whole AST and always goes into the more nested element, and basically visits all the nodes in the AST, traverses all the nodes in the AST, building something called tree path along the way, but that's not that much important at this point. This is a bit different from the elements because trees don't have enclosed trees. It's basically the API to work with the AST is more built on visitors, and it's basically necessary at this point to use visitors or scanners to actually work with the API to visit the ASTs. And as we have seen, what we are looking for is our method invocations. So we basically take we extend the scanner, which will go through every node in the AST. At some point, it will visit, it will see a method invocation, and this method will be called. And so all we need to do is to add some verification to this in this method. And what we do is that we use yet another utility class that is called tree that allows us to map from an AST node into one of the attributes attached to the node, which is the element that is being used at that place. For methods, the method that is being called at that place. And this method is getElement, so we are holding the element for the method that is being called, and we just see if it's the method that we don't want to disallow, that we want to disallow or not. So we will check the name, then the parameters, if there are no parameters, and we will check the owner of the method. And if it's this to lowercase method without any parameters on string, we will print some error. We can use these trees to print messages which are more precise. It allows us to put errors at a specific AST node, which is more precise than what we can print in the annotation processing API. And there are many more methods on the utility class. Some of them are really powerful. We can get, for example, the documentation comment for a given AST node and so on. And yeah, in case you would wonder, sometimes the attributes are a bit weird. So sometimes the get_element method can say null, we don't know what's being called here. So it's sometimes good to check for null for the elements written for a particular AST node. And now we can try to build this, and let's see. And I guess I need to clean build. And yes, it will produce the error for us. And yeah, I guess I will stop here. I could show you how the validate method is from where it's run, but it's somewhat similar to how we ran the compilers using the compiler API, the way to invoke the compiler. So let's skip that, and yeah, we can get to the questions if there are any, and there are some. That's good. So let's try. What's the common way to generate code via annotation processing? You use string replace method. To be honest, like what you need for the filer API is basically a string or bytes. So whatever you want for the way how you get the string, it's up to you basically. I did it the most simple way. If I had something more complex, I would probably use some templating engine, I guess. I hope that we will get some maybe nicer way to do it than just replace in time. So let's go to the next question. How the ID compiler is configured to use your compiler plugin? That's a good question, that's something I forgot to say. So let me switch back here. How do we run annotation processors in the compilation? Let's do it on the command line. It's actually not difficult. We can do, if we place a jar with annotation processor on class path, it will be automatically run. So what we can do is I have some jar here, and now what I need to do, I need to provide some input here, and I should uncomment these so that we see some output. So basically, if you want to run an annotation processor, it's enough to put a jar with the annotation processor on class path. There are other options like put it on a processor path, which is a special path only for annotation processors. If it's in modules, it's a module processor path. And basically, in your framework, in your build system, Maven, whatever, anyway you put it on the class path or the other path will be okay to run the annotation processor. It will be, if it's correctly registered in maintain services or module info, it will be automatically found and invoked. Okay, let's go back. Is runtime AST possible? If you mean AST for the bytecode that is running, not at this time, or no, depending on how you look at that. But you could, like, if you would have source code, you could get AST for it using the APIs, but not that would be for the source code, not for the bytecode that is actually running right now. That's not possible at this time. What do you think about Google's error prone? I believe it's also written on these APIs. That's at least what I thought. So, good. Can the source API be used from other entry point and annotation processor? It seems like a workaround. Yes. There are, either you can like invoke the compiler yourself, and then you get control over the compiler and you can get the ASTs, or Okay, if you want the standard, okay, I should go back probably one step. If you want the standard way, I don't think there is any other way than annotation processing. If you would be okay with using javac APIs, then yes, you can either use like more detailed API to control what the compiler is doing, or you could use plugins for javac, which again give you more detailed way to see what the compiler is doing, basically, and plugging yourself at more specific place in the compilation pipeline, basically. Did I understand correctly that the AST API is public but not standardized? So yes. Yes, it's not standardized in the same way as the annotation, as the Java language model API or the annotation processing API, but it's public inside JDK. So if you are fine with using like JDK specific APIs, then it's there. The lowercase example, as it's written, it wouldn't work on JDK 7, but I believe it, as it was written, I believe it should work from JDK 8 upwards. So yes, it's a JDK specific API that is only for javac, basically. Can we load classes and use reflection API via processing env or file during validation? Like, I guess yes. Like, or no. Okay, let me read this again. Like inside an annotation processor, you can of course like load classes and use reflection, but not that much directly using processing environment. You basically do it like inside the annotation processor, yes, but the model API is not really the way to do it. I'm not sure if I understand this question quite well, but so I don't know. Okay, thank you for your attention.